Hey, welcome back to Math with Patrick and Quill. Today is November 28th, and we're solving problem 332 from the Daily Epsilon calendar. And we should show why the answer today is 28, because that's today's date. And this diagram has been confusing me. I've been looking at this on my own for a little bit, and I kind of came to the conclusion that the premise is wrong. Let's go over it together. So we have this rectangular pyramid. We have a rectangle on the bottom, and then all four of these vertices connect to this apex or top of the pyramid, and we have different lengths for these kind of diagonal edges here. There's one with a length of 1, 4, 7, and then finally 8. And the problem is telling us that all edges of the rectangular pyramid have integer length. So far we have 4 integers, but then we'd also know that this side, given that it's a rectangle, they're going to be the same length. And then also just given from this prompt, we know that this is going to be an integer as well as this kind of depth distance here. And the issue, I'll just kind of, maybe not prove, but explain maybe just kind of geometrically. So let's take a top-down view of this pyramid. We're going to have a rectangular base. It's going to connect kind of right here as the apex. Here's my length of 1. Here's 4. Let me draw that 1 a little bit better. I'll just do this. Here's the 7. And then finally, here is the 8. And the issue is that looking at this pair with the 1 and the 4, the 1 is shorter. Therefore, the apex of the pyramid needs to be closer to that vertex than the bottom one. However, if we look at the other pair, the 8 and the 7, the 8 is longer and the 7 is shorter. Therefore, the apex needs to be closer to the bottom left corner. And it's kind of like we have a contradiction here. Like, how could we be closer to this top right corner and like in comparison to the bottom right corner, yet also closer to the bottom left corner in comparison to the top left? Like, this setup would suggest that we would need to switch, for example, the 8 and the 7, because in this case, this 8 is like pushing this apex further towards the top of our diagram, just as this 4 is also pushing it further up in the diagram. I was also looking at other like proofs of this, and I believe for whatever reason that these two numbers squared, or the sum of their squares, needs to be equal to the sum of the squares of the other two numbers. Although I wasn't really able to figure that out on my own. I mean, if we do 16 plus 49, we do get 65. And then if we do 8 squared plus 1 squared, we do get 65. So there's some merit to this. I just wasn't really able to figure out how to prove it to myself. I think there's some like Pythagorean theorem involved, maybe some law of cosines involved, maybe some stuff with vectors if you wanted to. Either way, we do need to swap the position of the 7 and the 8 for this to make any sense. Again, I'm kind of relying back on the idea that the 8 needs to be here to push the apex closer to the top of our diagram, because the 4 is also doing that. So that being said, now we just need to use, I think, a triangle inequality theorem, or the triangle inequality theorem here, and then we can just solve the problem pretty quickly. The idea is that this face on the right side is a triangle. And I know that it's not perfectly like top down in real life, right? We would kind of be viewing this triangle from the right side, but it still is a triangle. It still has a length of 1, and then I guess 4 would maybe be here, and then this base is the length that we don't know down here. And given that it's a triangle, we know that this mystery length must be greater than 3 and less than 5. The idea here is that if we place this 4 and a 1 in a straight line, then we'd have a length of 5. Although if we tried to connect these endpoints, we wouldn't be creating a triangle anymore. This would just be a line segment. So we do need the 4 and the 1 to have some kind of angle here that's not 180 degrees, and that would just barely decrease this 5 to something a little bit lower. So we could imagine that this mystery length is the longest length of the triangle, and therefore it needs to be shorter than 5. Or maybe the 4 is the longest length of this triangle, and therefore this length does need to be greater than 3. Because, similar reasoning, if it's exactly 3, then piling a 3 and a 1 and a 4 on top of each other is just going to give us a line segment, not a triangle. So basically, we have figured out that this mystery length must be 4 itself, because we have integer side lengths for our pyramid. So 4 goes there. And for the same reason, we can take a look-see at this top triangle right here. It's going to have a length of, well, the problem statement says 8, and I'm just ignoring that because it should be the number 7. Then it has a 1 right here, and then this mystery base is this length that we don't know in our diagram. And by the same triangle inequality theorem, we know that this mystery length must be less than 8, but also greater than 6. And the only integer that does that is 7. So this length here on the base of a rectangle is 7, and if we're trying to find the area of this rectangle, we can just do 7 times 4, which does give us 28. So I'm a little bit unsatisfied here. I'm still not even sure if all of these numbers are allowed to create a rectangular pyramid here. Maybe there's some internal goofs that might happen with the Pythagorean theorem or the law of cosines or vectors. Although I think what I mentioned earlier, how the sum of squares of these opposite sides is the same, I think that makes this a valid diagram. Again, I'm not quite sure about all that. If you have a proof that you'd like to share, please comment it below. But either way, just by using the triangle inequality theorem, we have shown that the only possible answer would be, 7 and 4. So the only possible answer is 28. And I'm calling this good enough. So here's my solution. Hope you enjoyed, and I'll see you tomorrow. Bye.